by Kim Robertson, an arrangement from a traditional Shetland Islands. And as usual, I always like to end with Kathleen by Lori Bradley. Fairy done. Happy Halloween, everyone. What am I doing? I knew I want to see.
Have the volume all the way up.
Can you hear us? It's not muted. Thank you very much, Kim.
Oh, you're so very welcome. It's a pleasure.
Thanks. Sorry, we have somebody talking in the background. Thank you again very, very much. And it's always such a pleasure to hear you. And thank you so much for being willing to come back every month.
Well, thank you so much for having me. It's always a pleasure being with everyone.
Great. Well,
Thank you.
thanks. And welcome, everybody. This is the October meeting of the Orange County Astronomers. I am very happy to welcome all of you here. I'm Barbara Toy, the current president, and we have a really great lineup of events tonight. And so I think that probably, rather than wasting time with saying anything off the cuff or whatever, I'll just turn it over to our announcement crew. Take it away, Ceci.
Kyle, you have the things, right? to present?
Yeah, I just forgot to end
Okay.
the first slideshow.
Awesome.
Here we go. And oh, I have no video. Okay. Well, anyway. Oh, there we go. Perfect.
Paloma. Yes. Okay. Hello, my name is Paloma, and I would like to welcome all new members. Thank you for joining us, and make sure have a wonderful time.
So star parties are still mostly on hold. The ANSA star party, they're getting ready to resume. There have just been some issues about getting dates and getting it started right away, but please check the calendar because they will be starting them soon. So you can see the astrophysics special interest group meeting is happening back at the Heritage Museum at 7:30 on October 21st. Those are pretty much back to normal at the museum. The beginners class and the board meetings are still online. Again, check the calendar for everything and online, and all the club events will be on the calendar.
Okay, so for outreach events, they're starting out. We're super excited to do this. Cecilia Caballero will be the outreach for now, and you could email them or her at outreach@ocastronomers.org. Also looking for volunteers. So if you guys are open to going to classrooms, and please reach out to us to add you to our list. Thank you.
So for the Adopt a Scope program, you can now look online on your computer at the current inventory. You can do that by going to the website, and then under resources, there will be an Adopt a Scope tab. There on the top left, as you can see where it's circled, you can download the current inventory and see that along with printing out an scope adoption agreement if you're interested in seeing what that contains as well. For anything of interest that you'd like to put in the Serious Astronomer newsletter, which is the club newsletter, please send any items of interest to Dave Fisher and he'll review those for you. If you're everyone is still getting a printed copy of the newsletter, but if you would like to opt out of receiving a mailed copy every month, please email Charlie and he will stop mailing you a copy. Everyone always still has electronic access to the newsletter at the club website. Please remember to clear your weeds at ANSA if you do have a pad, despite star parties still not happening on a regular basis out there. Weeds never go away.
Hello, my name is Galila, and today's month is gonna be a winning givers, and hopefully you guys see the beautiful moon. And good night.
So the next general meeting will be November 11th. And John Garrett is up next with the What's Up presentation.
Oh, hello. Thanks for having me back to do the What's Up. I find them very motivating. If it were not for doing these What's Up, I wouldn't find the time to get out sometimes and get pictures of the night sky. So I'm actually in your debt for giving me that motivation. The some things I'll show you for this time. Oh, I took most of my pictures about 3 weeks ago when I attended the Joshua Tree Night Sky Festival. So almost all the pictures I'm going to show you tonight are wide field shots I took then, plus a few that I had to slip into to make up everything that's there. But here's the Sunday night, the night after the main event at Joshua Tree, where they had a much lower key star party at the Indian Cove campsite, which is near 29 Palms. And so I got a little picture of the Earth's shadow rising. And only later I realized that there's some interesting coincidence with my putting an Earth's shadow in this picture, but I'll come to that at the end of the talk. A little bit after that photo I just took, I noticed that Jupiter was rising. So Jupiter is just past its opposition, which means it rises at about sunset. And here it looks like it's just risen, but it actually has risen a little bit ago earlier, but it's the mountains. It had needed time to clear the mountains, but by the time it clears those mountains, it's getting plenty dark. It makes a good object to look at, though low in the atmosphere, but it does stay up high throughout the night. So this really does turn out to be a good month to set your telescope at Jupiter. And if you looked in the other direction of Jupiter after it gets dark, you might notice a very familiar asterism of the Big Dipper that is setting for the year. So you won't see much of the Big Dipper for a while. And then if you look to the south, you might see the last of the bright spot of the Milky Way going below the horizon near just after it gets dark. And here in this picture, I've got just a few highlights that I shared last month, and you can see the teapot shape of Sagittarius descending into the southwest now. And I'm going to use that picture, and I'm going to stitch together 3 other pictures taken that same night and some of them later in the night to get a little panoptic view of the ecliptic. And so here's 2 other pictures that I took, and I stitched them together roughly by overlapping stars in the corners. And there's some distortion between pictures, but you get the idea. And so the next, right after Sagittarius, is the constellation Capricornus, named after the sea goat. When I figure out what a sea goat looks like, I intend to draw a figure for it, but I haven't figured that out yet. And then next is the constellation Aquarius, which is one of those constellations I've had trouble believing in, but apparently it is there. I've never been able to get a full framed picture of it because whenever I go out, I usually can't tell where it is. And so after I check my photos, I often don't have the whole thing in one photo. And then over here we have Pisces and Cetus the whale. And the most prominent object that you'll see among those constellations is, of course, the star, the bright star, which is actually the planet Jupiter. And so that's Jupiter. Again, it rises shortly after, rises by sunset, but it's up in the sky all night. And then Saturn is also easy to spot in the early evening too. And these 2 diagrams I created of Jupiter and Saturn, they're to scale if you're looking through an eyepiece at those. So that's how their relative sizes would be. So it's very likely if you get out, you will look at both of those and you can compare that Saturn is just a little bit smaller than the apparent diameter of Jupiter right now. And Neptune is right in there, not to scale, definitely not to scale, but that's about where Neptune should be. And in fact, if I blow up this little picture, there's a tiny blue dot about where I think Neptune is. So I might have been able to pick up Neptune with my 24mm camera lens. And then the ecliptic traces this line, and that's the path the sun takes yearly, and it's the approximate path in which you will see the planets. And if we look at that middle frame where I had Saturn photographed, here's the constellations around Saturn. And so if you have a telescope at Saturn, you might as well take a look at some deep sky objects in the area. M2, the Saturn Nebula, some M73 and 72, and the Helix Nebula. Of these, some of my favorites are M2. It always shows up well in a telescope, and it seems in my experience a lot of people have overlooked it because this time of year everyone wants to see their last views of Hercules, the Hercules cluster, M13, while it's still high in the sky. But if you throw your telescope over on M2, it will not disappoint. It shows up pretty well in a variety of scopes. The Helix Nebula, I don't recall seeing it in a telescope. I'm told that it's rather bright, but it shows up really nice in short photographs this one here was taken through my 3-inch telescope. So even a minute photograph, you'll see something that you can work with. And then of course the Saturn Nebula shows up as a very bright dot. The real challenge with seeing the Saturn Nebula is seeing those protrusions that give it its name, the Saturn Nebula. But you need a pretty powerful telescope to see that part, but it's definitely worth a good look. And then these other objects are less exciting compared to those other three, but there are 2 of them are globular clusters. You definitely need at least an 8-inch or larger telescope in a dark sky. And M73 appears to be a catalog error that today we would not have classified it as a Messier object, but it was in the catalog a little cluster of stars. And again, nothing's to scale. Then we go to that frame where I had a photo of Jupiter. And here's the constellations Aquarius, Pisces, and Cetus the whale. And near Cetus, there are 3, maybe 4 things of interest, but 3 that you can see. One is that star, which is supposedly the most distant star ever detected and named Arundel. I noticed that that's its coordinates. And so if I got that right, that's where it is. You can't see it with an earthbound telescope. You need one in space for that, but it's nice to know that's where it is. But the other objects that are fairly bright, the Sculptor Galaxy and NGC 253. I took this photo, I think, with my 3-inch telescope. And then NGC 247, I took that under poor conditions with, I think, the same telescope. And then NGC 246, you really can't see in my photograph, but I can see it when I zoom in. And it's a planetary nebula. And I have a thing for planetary nebulas. I think they're just the most fascinating things to hunt down. So this is going to be my project this month to try to get a decent photograph of this planetary nebula. And again, a planetary nebula is a star comparable in size to our own star that has died and blown out its outer layers. And that's what we see as the nebula. And if you continued along the ecliptic, you'll eventually come to the constellation Taurus, in which you'll find the Pleiades star cluster, but you'll also see bright red Mars. And the Mars is beautiful. 3 weeks ago when I was taking these pictures. And it's a good chance to compare red Mars to red Aldebaran, which is the eye in Taurus, the bull, as I've drawn here. And so there's Mars. And sort of a short-sightedness on my part, I realized that the planet Uranus is just off the field of view of which I took this picture, and I never took a picture aimed up just a little bit higher to capture Uranus, but that's about where the planet Uranus will be. And that's really a shame because that's also where an eclipse is going to happen. Next month on the morning of the 8th, you'll see a lunar eclipse, which again, those things are one of the most beautiful objects, beautiful opportunities in the sky. But I believe the total darkness period for it is going to be from 2 to 5 a.m. 3 o'clock is going to be the, actually 2 to 4 a.m. is more, about right, yeah. The peak is 3 o'clock. I think I wrote 5 incorrectly when I said 5 a.m. So if you're going to get up and see this thing, definitely be looking by 3 o'clock in the morning. And so set your alarm on the 7th. Now, though I didn't think to photograph where the moon would be, it's going to be just like a little farther off this picture here. I did photograph last year an example of how this eclipse will probably appear. And so the moon is going to pass fairly close to the Pleiades star cluster. So with a wide field camera, you should be able to get a picture of both of them. This was taken last year with a telephoto lens, and I don't remember what setting I used, but essentially I was able to pull in or out the telephoto lens till I got both framed, and I bet you'd be able to get the same this year. And so this is one of the first eclipse pictures I ever took. It's from my backyard where I still live now. I took it with slide film, and there's scanning artifacts in it. But I think the moon is going to be about in the same position for this eclipse as it was on this one that I took 20 years ago. And so the tree is still there. The horizon line is still there. My only question is after 20 years, whether the stars are still going to be there. And so I'm going to try to get a matching photo of my lunar eclipse 20 years apart. And I I'm afraid I'm going to have evidence for how much light pollution has been added to my community, but I plan to use that in some of my materials that I'll be sharing throughout the community to raise awareness of what we just had 20 years ago and that we can get it back with a little more attention. Anyway, or just below Taurus is also Orion. So maybe around 10 o'clock or so, you'll start to see the constellation Orion rising. And next weekend in Orion, that's the radiant of the Orionid meteor shower. And it doesn't sound like a super powerful shower, but I guess the peak at best is probably 20 meteors overhead per an hour. And so I believe it's going to be a very dark weekend. So if you're out that weekend, it might be a good time to beat the crowd, get out before the weekend and set up a camera or look up in the night between 12 and 3 o'clock in the morning, or even after the moon rises at 3. I bet you'll still see meteors if there's any to be seen. And when I first showed you the picture of Sagittarius, we went kind of left from Sagittarius. If you went sort of right, you'd end up in the constellation Aquila, the eagle. So that's still in the sky, though it sets earlier. And if you continued up Aquila, you'll still be able to see the path of the Milky Way. So this time of year, even though the bright center of the Milky Way is going below the horizon, the Milky Way still takes a path almost directly overhead, in which case here you have Cygnus the Swan, which continues up from Aquila, and then it's got Delphinius and Cygnus there. So as long as you've got Cygnus the Swan overhead in the sky, you can always find some interesting stuff to see in the Milky Way there. And then continuing a little farther, you'll come to Cassiopeia. I didn't draw any parts of Cassiopeia, but you can see Cassiopeia as a sideways W in the middle, and then below is the double cluster rising in the northeast, and then off to the right, you can see the Andromeda Galaxy M31. So that also shows up fairly early in the sky this time of year. And just before tonight's program, I learned that there was a flyby of a space probe named Lucy that is possibly visible from our area. And so I pulled out a picture I've taken of Cetus the whale sometime earlier in Pisces. And this area right here, if I got my information right, according to NASA, is where you may see the space probe Lucy as it gets a gravitational assist from Earth emerge from the Earth's shadow. And so here you're watching the satellite to emerge from the Earth's shadow. And the time that it does that for our location will be around 4:26 a.m. So if you are photographing that area, suddenly you might get this object. And though I've photographed almost too many satellites for my taste, I've never photographed an interplanetary space probe. So this may be your first chance to observe or photograph one. And anyway, the interesting coincidence was that I'd already put in Earth's shadow picture at the beginning of my talk. And then when I added this one just about 15 minutes before we started here, I realized that's also an Earth shadow thing. The satellite, the space probe is going to emerge from Earth's shadow as it swings close to Earth. And that's the direction to watch. So again, thank you for letting me do these opportunities. I can't thank you enough. And so my thanks is not to scale for what I feel. Thank you.
Thank you, John. Your presentation always have this quality that really takes us to the journey, and I really feel that it's as if I'm right now outside and observing. Thank you very much. We're really grateful for having you and you doing all these presentations. So I would like to say hello, everybody. My name is Reza, and I'm the Vice President of the club. And I, too, would like to welcome you to October 14th, 2022 General Meeting of the Orange County Astronomers. Let me actually change the view here. That we have some good news for everybody. If you could see the one of our attendees, panelists here, is actually a group of, let me spotlight you for everybody. Okay, great. So we have got our agreement well worked with Chapman, hopefully, and hopefully we'll be able to restart our hybrid meetings in person and online pretty soon. Please check our website and the mailing list for the news when you could join us in person also. So right now we have a small crew there at Chapman testing things out, making sure it all works for resuming that. Okay, great. So with that news,
Raisa, before
yes.
you leave that issue, the one thing we know for sure is that we will not be meeting here in November because we don't have access to the hall in November. So we're hoping that we will be back here in December with the hybrid meeting. But as Raisa said, please keep an eye on the Serious Astronomer and the website and all of our other information sources, and we will keep you advised of what's going on. And by the way, at this point, unfortunately, because of Chapman's current rules, we will not be able to have any minors attend our meetings until we're able to make appropriate insurance arrangements, and that we're working on. So again, we'll keep you advised of what's going on with that. Back to you, Raisa.
Sure. Thank you very much, Barbara. So let me go ahead and without any further ado, introduce our main speaker for tonight, who's actually a native Southern Orange County person. So he is a postdoctoral researcher at Stewart Observatory at the University of Arizona currently, where he studies various types of stellar explosions. He was previously a postdoctoral researcher at the Center for Astrophysics, Harvard and Smithsonian. He received his bachelor's in physics from UC Berkeley in 2012 and his PhD in astrophysics from UC Santa Barbara in 2018. Please join me in welcoming Dr. Griffin Hosseinzadeh. Griffin.
Hi, everyone. Very happy to be here. Thank you so much for the invitation. Can everybody see my slides okay?
Yes, we could see them all good.
Great. So I'm going to tell you a little bit about basically supernovae and other types of transients, which is what I work on. I'm an observational astronomer. Recently, these things, there have been several just in the last few days that I was very busy working on. So a little bit of background. A supernova is just a fancy name for an exploding star. You can see this artist's impression of what that would look like if you could really be right up next to it. You've got a star that's just sitting here and suddenly it actually explodes. And this is kind of in a real time type of thing, right? So this really just takes a few seconds to explode. You can see the time, if you see this little graph in the bottom right-hand side here, this video that I just showed is supposed to last like an hour in real life. But really, this is a very catastrophic explosion of a star. And this will just keep expanding, as you see here, until it reaches something that looks kind of like this. This is called this is a nebula, but it's called a supernova remnant, meaning that this is what's left over after that star exploded, kept expanding outwards for hundreds of years. And all that material that was in the star and the material that was produced in the explosion turns into a nebula like this. This probably, you know, as amateur astronomers, you're usually better acquainted with the night sky than the professional astronomers. So probably many of you know this, but this is the Crab Nebula, which is a real supernova remnant. Currently, you know, this supernova happened about 400 years ago. Currently, this is about 11 light years across, just to give you a rough idea of the expansion rate. I'm going to zoom in on just the central portion of it here and show a couple of videos, but these are like real data videos showing the central region of the supernova remnant. What you see here is on the left-hand side, the view in X-rays, and on the right-hand side, the view in visible light. What you see is at the center, there is a star there, and that star is a special kind of star, which is a neutron star, highly magnetized and spinning around. We call that a pulsar, and you can see why from this video, because it is actually pulsing in a sense and affecting the gas that's around it. These ripples that are kind of going through the gas right outside that pulsar. Again, this is real data that was taken, and you can see actually in the X-ray side, it's also launching a kind of jet, a bipolar jet outside in the, you know, along the direction of the spin axis in the X-rays. If you really want to know why it's called a pulsar, you can actually look at this video in the infrared where you can actually see this star pulsing. This is how it got its name, but of course you can observe it at many different wavelengths, not just the infrared. So with that little bit of background, I want to go over what kind of things we can learn from supernovae and other transients. This touches almost every aspect of astrophysics, which is why I love it. Nuclear physics, stellar evolution, galaxy evolution, all the way up to cosmology. So this is from the smallest scales, the nuclei of atoms, to the largest scales, which is the entire universe. I'll start with nuclear physics. So inside of a star, this is before it explodes. Inside of a star, nuclear fusion is happening at all times. When stars are formed, they're made basically just of hydrogen and helium. What I'm showing on the right-hand side here is the main reaction network, at least that stars start out with, which is just hydrogen atoms combining to form deuterium, which combines with another hydrogen atom to form helium-3, which combines together with another helium-3 atom to form helium-4, which is the most common isotope of helium. You may notice here, I don't expect you to remember all of these reaction networks, so don't worry about that. But the main point here is that during these reactions, you release photons, and those photons are the light that we receive on Earth. That's sunlight. So obviously very important to humans that this happens. And you may notice another thing here, which is that in addition to the output being photons, there's an output of extra hydrogen atoms, which then will go back to collide with other hydrogen atoms and continuing this process. So this is why this process can last for a really, really long time until you essentially run out of the fuel, because it kind of is a chain reaction that feeds itself. Now, this leads to very extreme conditions in the center of the star where this fusion is happening. 30 million degrees Fahrenheit is roughly the temperature, 250 billion atmospheres of pressure. So this is, atmosphere meaning the atmospheric pressure on Earth at the surface of the Earth. So this is something that is really, really extreme, and something that none of us, except maybe a few of us, I don't know, will ever encounter on the surface of the Earth. But this brings me to a little aside, which I think is really cool. One question is, can we do nuclear fusion on Earth? Some of you may have heard about this in the news, that this is a potentially very, very enormous source of power if we could do fusion on Earth, and a clean source of power. In fact, it's nuclear energy without the radioactive waste, which would be really, truly amazing. But it's very difficult to do because of those extreme conditions that I discussed. I had the privilege of touring this facility at Lawrence Livermore National Lab. It's in the Bay Area, just like a couple of hours east of San Jose. And they're trying to do controlled fusion there, where they have a very, very tiny target here. This target you're seeing is like smaller than the tip of my finger of hydrogen. And then they have the rest of that building essentially is filled with gigantic laser banks, where they're just trying to put so much power focusing down onto that very, very tiny target of hydrogen to ignite it and produce nuclear fusion of the hydrogen target. So this hasn't, you can do fusion, but of course you need to have it be controlled fusion in order for it to be sustainable and not just blow everything up. So that we have not been able to do that yet, but people are still working on it. And I think that's a very exciting topic outside of astronomy completely, but not totally, because if we could understand exactly the conditions inside of stars and supernovae, then maybe that would help us do this on Earth as well. Talked about the fusion of these low mass elements, hydrogen into helium, but in fact, more massive stars, so that's basically what our sun does, it just turns hydrogen into helium, and it does actually one step after that of fusing the helium together also. But heavier stars that are like 8 or more times the mass of the sun, roughly, make even heavier elements. So the sun will end up as a carbon-oxygen core, and that's it. It won't be able to go any further than that. But if stars are more massive, then they can actually produce even higher temperatures and higher pressures in the center. So what will happen is, you'll fuse the entire center of helium into of hydrogen into helium, and then you'll start doing helium fusion, turn that into carbon. Carbon fusion produces neon, and so on and so on. You can see how this builds up kind of like an onion structure. This is not to scale what these shells look like, but the order at least is correct, that you end up with a bunch of different elements up until you get an iron core. And now iron is a special element because in order to fuse iron together, you have to actually add energy. So whereas before, when I put two hydrogen atoms together to produce helium, that released energy. But when I put two iron atoms together, it won't do anything unless I add energy to it to fuse those together. So during the lifetime of the star, you see that the center is always producing energy. And in fact, that is what keeps the star in its static state of, it doesn't change very much in size. If there were no fusion happening, what you would find actually is that the star would collapse under its own gravitational pull. The outer layers are attracted by the inner layers, so therefore they would just fall in. But because we have these very high temperatures and pressures in the center of the star, which are produced by the fusion, you also have gas pressure, which is holding up the star from falling together. So what happens now, I discussed, once you get to iron, there's no more release of energy. So you just release, you get rid of this gas pressure. And you can see based on these arrows, what's going to happen is the star will begin to collapse. Now, in some cases, you will get to a state where it collapses, becomes even more dense. There are stages where it collapses and becomes even more dense and starts new fusion, but eventually you'll get to the point where the fusion won't happen anymore. There is a state called quantum degeneracy pressure. I'm not going to go into the details of how this works because it requires quantum mechanics. I probably couldn't actually explain it to you, even if you asked me. But there is a situation where you cannot push the atoms closer together anymore. Quantum mechanics just says that's not allowed. So up to about 1.4 times the mass of the sun, the star can be supported in this way. I'll come back to that later. That's called a white dwarf star, where it's just a bunch of atoms, very, very dense, but held up by electron degeneracy pressure. You can go a little bit heavier than that, up to about 3 times the mass of the sun. And you can have a neutron star, which is supported by neutron degeneracy pressure. But anything above 3 times the mass of the sun, even that goes away. And so then the only thing left is for all of this material to just collapse and form a black hole. So this tells you basically the 3 end states of stellar evolution. You can either get to a white dwarf, a neutron star, or a black hole, depending on the initial mass of the star. So for a star like our sun, our sun will never actually explode as a supernova. What happens is as it reaches its last, say, million years of life or so, it will kind of get in this unstable state where it starts throwing off the outer layers of the sun into a nebula, pretty much like the one that you see here called the Ring Nebula. The reason it's called the Ring Nebula is because it looks like a ring of material, and that is because the star actually just threw that material off in its kind of death throes. It's a nice metaphor. And then at the very center of this, you see a white dwarf, which is the remnant, the thing that's left over after it lost all of its outer layers. It's essentially just the core of the star. A white dwarf has most of the mass of the sun. Only those very outer layers were lost. But it's about the size of the Earth. So think about how dense that is. It's extremely dense, like nothing that we have on the Earth. And by the way, we call this type of thing a planetary nebula. You may have heard this term before, but very, very confusingly, it has absolutely nothing to do with planets. The reason it's the end state of a star has nothing to do with planets at all. The reason it's called a planetary nebula is because before people understood what they were, they thought it looked like a planet. It's as simple as that. Like it kind of was a puffy gas thing, And the only puffy gas things that we knew of were like planets like Jupiter and Saturn. So they were called planetary nebulae, and we never changed the name after that, unfortunately. So that's what we're stuck with. Now, for stars that are more massive than the sun, more massive than about 8 times the mass of the sun, as I said before, you actually do get a supernova where it goes all the way to iron, collapses, you get either a neutron star or a black hole at the center, and all of that material will kind of fall into the center, kind of bounce off of the central object and just explode outwards with incredible amounts of energy. And that's where you get these supernova remnants, like I showed at the beginning of the talk, like the Crab Nebula that you see here. And at the center of the Crab Nebula, you see that pulsar, which is a neutron star. Again, this is about the mass of the sun, about twice the mass of the sun in this case. All the rest of the material is in that nebula. But this thing is about the size of a city. So if you thought a white dwarf was dense, think about this. This is more massive than the sun and only about 10 miles across. When I presented this in Boston, I could say that it was the size of Boston, but you know, the LA area is much, much, much bigger. So you could fit several neutron stars in there, just in Southern California. So I skipped over one thing, which is that, you know, it's still true that our sun will not explode as a supernova, but there are situations where white dwarfs, which is what our sun will become, can explode as a different type of supernova. The last thing I discussed was called the core collapse supernova because it has to do with the core of the star collapsing. But here we have something called a thermonuclear supernova, and that is where something causes a white dwarf to essentially catch fire. It's not quite fire because it's not like in air, but it is more like a nuclear explosion of the material that makes up the white dwarf. These can either be triggered by 2 white dwarfs merging together, which you see in the left-hand column of this diagram, or it can be something like a more normal star, like a sun-like star or even bigger, which is transferring material onto that white dwarf if they're in a binary system. And that material kind of ignites the white dwarf to explode. That's the right-hand column here. So actually either or both of these processes might happen to white dwarfs in binary systems, and we're still not sure which one it is. It could be exclusively one, exclusively the other, or there could be both of these happening, and this is an active area of research. We actually don't know which one of these is what causes the supernovae that we see. So the important thing here, coming back to nuclear fusion, is that, you know, the star produced elements up to iron. You see that here in the yellow elements. This is the periodic table. Probably most of you are familiar with it, but it shows all the elements that exist in the universe. What you're seeing here is hydrogen and helium in blue. Those existed from the beginning. Stars produce most of the next set, all the yellow ones, which are produced in the supernovae, in the star themselves. But then the supernovae, when they explode, remember I said iron needs an energy input to do fusion. Well, an explosion of a star is a pretty good energy input. So when you do that, you can actually cause fusion of iron and heavier elements. And then you get all of these things which are colored yellow and green, which are coming from exploding stars. I will come back actually to the rest of the periodic table towards the end of the talk, which is the whole purple area. But the first 4 rows of the periodic table basically come completely from stars, either the stars themselves or the explosions of the stars at the end. So another thing that we can learn about, and this is actually what I'm most interested in my research, is learning about stellar evolution. How do stars form? How do they live? And how do they die? And learning about these from supernovae. So to give you an idea of how we do this, I'll show you, so far I've been showing you, first of all, pretty pictures of dead stars and simulations of what the supernova looks like. But here I'm going to show you an actual image like what we see. So this is a beautiful spiral galaxy. This is not very far outside the Milky Way. And you might notice these little crosshairs in the near the center. Let's see, I don't know if you can see my mouse, but it's about in the top left of the galaxy.
Yes, we can see your mouse.
Yeah. So watch what happens as this video plays. You see in the crosshairs, a point of light just suddenly appears and it kind of starts to fade away. So this point of light is a supernova. What happened is, at the beginning, when you see just the galaxy, you can't see that star that is going to explode. All you see is the trillion stars that make up the galaxy light, but you can't see them individually. And then suddenly you see a very bright new point of light, which over the course of a few days gets to its brightest, peaks, and then fades away. And if you look very closely, this may be hard to see on the screen, but the supernova actually changes color too. It starts out very blue and then turns kind of more reddish towards the end. That is actually real too. That's not like just an artifact of the screen. That's because early on the supernova is very hot, and so it glows blue. And then as it cools off, it starts to glow red instead. And it's still, thousands of degrees. So very, very hot compared to anything on Earth, but colder than it was to start with. So this brings a very important issue, which I'll come back to later in the talk also, which is that we don't know which star is going to explode at which time. So we have to be always looking in order to find these supernovae. I'll come back to that at the end. But one of the most important tools once we've discovered the supernova is something called spectroscopy. Many of you, especially if you have a science background, may be familiar with this. Essentially, the idea that you can take light and break it up into its component colors. So here you see, just a white light being shown into a prism, which breaks it up into a rainbow. Hopefully you've seen this in real life before. If you haven't, you should check it out because it's so cool. But if you shine something that is not white light, but consists of a bunch of different sources of light, you may see instead something like this. This is called an emission line spectrum, where you just see certain wavelengths of light, but no other ones. So I see a line of red, a line of cyan, a line of blue, a line of purple, and a few other fainter ones. So this emission line spectrum is what happens if you just take pure hydrogen gas and you make it glow. It will look like this. So you won't have a full rainbow, but just certain wavelengths. And the nice thing about this is that if you see those wavelengths, you know you're looking at hydrogen. People describe this as like a fingerprint elements, right? Where this is a unique signature of hydrogen if you see these wavelengths of light and only those wavelengths of light. And we can go back to our periodic table. Every element has an emission line spectrum like that, which is unique. So when you think about observing supernovae with spectroscopy, what you're doing is looking for these patterns of light and trying to figure out what elements are the ones that produce those lines. And by doing that, you can figure out what elements are present in the supernova, which is very important to figure out what's happening. If you want to know, first of all, what type of star was it that exploded? And second of all, what are the products of the explosion? What elements did it produce during the explosion? So astronomical spectroscopy is very important. This is like, I would say the main tool actually in modern astrophysics is taking light from that supernova, which comes through a telescope, putting it through a prism and recording the emission lines and absorption lines you see. So some of the things that we observe in supernovae, some contain no hydrogen. And that's very strange because hydrogen is the most abundant element in the universe. Almost everything has hydrogen in it, in space at least. So to have a star somehow explode and there be no hydrogen present, that's quite a mystery. They have different behaviors too. Some fade after just a few days. Some can keep going for years. You can observe them for, even a decade in some cases. Trying to understand why those are different from each other. What kind of star produces the fast ones? What kind of star produces the slow ones? Very, very different luminosities. Some are 100 or even 1,000 times brighter than others. And we'd like to understand what causes those differences. We see material moving at very different speeds, 100 kilometers per second up to 10,000 kilometers per second. Kilometers per second is very fast, by the way, for anything on Earth. But in space, 100 kilometers per second is not that fast. And in some cases, we even see things that we think are asymmetrical explosions. You would think that if you have a spherical star explode, then the explosion should be spherical. But there are many cases where we see evidence that that's not the case. So we'd like to understand, how does that happen? Is there an off-center explosion or something like that? So in all of these, all of these facts, we'd like to be able to connect the things that we observe in supernovae back to what the stars were that exploded. And again, that's because we almost never know what star it was beforehand, because we didn't observe it directly. We just saw a supernova happen. And so we have to use this indirect evidence to figure out what star it was that exploded, which we need, obviously, to understand anything about stellar evolution from the supernovae. You can also come at this from the theoretical side. People try to understand, how did the explosions actually happen? Theoretical astrophysicists can model this with computers, but in many cases they can't actually, they put in all the physics that they know, they can't actually achieve an explosion of the star. But I mean, we know that it happened, so they must be doing something wrong, and they'd like to understand what that is. Again, we know that stars kind of lose their outer layers, but the models of how that happens are not complete. We don't have a good model for what would cause a star to throw off its outer layer of material. I said before that some supernovae produce neutron stars and some produce black holes at the end. We'd like to understand what the difference between those is. And if, it may just be low mass things produce neutron stars, high mass things produce black holes, but actually there's some evidence that's not the case, that there's some mass range that produces black holes and a different mass range above it that produces neutron stars. As I kind of alluded to before, we don't know what triggers thermonuclear supernovae to explode, because we don't know what the companion is, if it's another white dwarf or if it's a normal star pouring gas onto it. And this is a tiny bullet, but actually a gigantic open question, which is that we know that many, if not most, massive stars are in binary systems. And so we have to understand how the binary affects the star that explodes. In some cases, there may be some effect, in some cases, there won't be. So from the theoretical side, we're trying to connect what we know about stars and supernovae to our understanding of physics. We know physics from first principles on the Earth, but these stars and the exploding stars are very complicated systems. So it's hard to always connect our observations and our theoretical models back to the actual physics that we know exists. So to make this a little more concrete, I'll give you one example of red supergiant stars. This is the star Betelgeuse, which many of you have seen in the night sky. It's one of the brightest stars that you can see. At the center is the star, but you notice there's a lot of material around the star. If you look closely at this, you can't see from the ground. You have to have a very precise telescope in space to see this, but it is a bunch of gas and dust surrounding Betelgeuse. Betelgeuse, being a red supergiant star, is mostly hydrogen and helium still, at least the outer layers. So coming back to this picture of the hydrogen emission line spectrum, when we observe the spectrum of Betelgeuse, or not Betelgeuse itself, another Betelgeuse-like star, which would explode, it looks like this. Now, what you're seeing here is a graph of the spectrum, where each one of these lines, going from left to right, which is blue to red, you see the brightness versus the wavelength. So for example, these really big lines near the center of the plot, those correspond to the brightness of that red line in the hydrogen spectrum. And so you can see, actually, these lines line up perfectly with many of the lines in these spectra, so we know there's hydrogen present in this star. These spectra were taken, a week or several weeks after the supernova happened. But one of the recent things that we've learned is that if you observe this type of supernova, which we know is a red supergiant explosion, very, very early, like within hours of explosion, you see something very different, which is there's very highly ionized elements that are not, they come in these narrow lines, which indicate that it's not moving very fast. So I don't know if you can see the labels on here, but carbon, nitrogen, oxygen, and the Roman numerals next to them is how many times you've ionized that element. So oxygen 6 means it's been ionized 5 times. This indicates really, really high temperatures, high energies, and really extreme conditions. What we think this is, so first of all, there shouldn't be oxygen and carbon at the center of this star, and nitrogen. But we think this material that's very close into the star is actually getting ionized by the explosion itself. And so this is actually, I've been telling you as if I already know this, but the way we know that this material exists is because we observe supernovae within hours and we see these very extreme emission lines of elements that shouldn't be there. So we think this is the material that is around the star before it explodes. But as you might guess, once the star explodes, it's going to run into this material and destroy it very, very quickly. So you have to observe this within a day or so, or else you'll never see it. I'll come back to this at the end of the talk again of how we're able to do that. It's been a huge advance in observational astronomy in the past decade or so. So stellar evolution, already very complicated and we don't understand it well. Let's move on to galaxy evolution, the next level up. Galaxies are collections of stars. So in some way, if we understand what the stars are doing, we'll understand what the galaxies are doing. But there's very complicated interactions there. So I've made this point several times already, but supernovae are very extreme, very extreme. So to give you an idea of that, I'm going to introduce a unit. This is a metric unit that probably most of you have not encountered in everyday life. The joule. Joule is a unit of energy. And to give you an idea of how, what this means for a human being, 6 gallons of gasoline, if you burn it, will give off about 100 million joules, 10 to the 8 joules. So that's a lot. Let's see, I'm going to work my way up to tell you how high we need to go to get to supernovae. So, wrong button. A lightning bolt, a single lightning bolt, gives off about 10 to the 9 joules. That's a billion joules. So that's like 60 gallons of gasoline. Of course, that's released in like a fraction of a second. So it's much more extreme than gasoline. This is going to escalate quickly now. The entire generation of electrical generation of the entire Earth in a century is like 10 to the 22 joules. So that's something like 10 billion times more than a single lightning bolt. And by the way, we've only been making electricity for like 100 years. So this is like almost all the electricity we ever produced. The annual light output of the entire sun, not just the part that hits the Earth, but the entire output of light is another trillion times higher than that, 10 to the 34 joules. If we take not just the sun, but all of the stars in the entire Milky Way, that's about 10 to the 10 times higher than that, 10 to the 44 joules. And that is roughly the amount of energy that's released by one supernova, 10 to the 44 joules. So, compared to anything on Earth, this is just crazy. It's kind of nonsense to even try to make the comparison and understand it intuitively. But one thing that I can say, the supernova will actually be as bright as the entire galaxy when it's active. You can think about it that way. This is why we can observe them so far away in distant galaxies, because they kind of outshine all the other trillion stars in their galaxy, just for those, months or years that they're active. But this is a really extreme explosion, like almost the same amount of energy as everything else that's happening. So given that there's this much energy released, maybe I can convince you that it is possible to affect how galaxies evolve, these supernovae actually do have an effect. What you can see here is a picture of a distant galaxy where there's this material being kind of ejected out from the center. That's what you see in red here. It's called the galactic wind. And we think at least one of the causes of this wind is the energy that's injected to the rest of the galaxy by supernovae. So supernovae, you know, in addition to producing all the elements in their nearby universe, they actually contribute to the energy of the entire galaxy. And they also put those elements that they produce out into the galaxy, which is very important for the chemical enrichment of the universe. And I'll just warn you a little bit, I realize that a lot of times, you know, in these talks about, people are trying to show you beautiful pictures of the universe. Everything kind of tends to look like a fuzzy blob of gas, which is kind of true. But remember that fuzzy blob of gas I showed you at the beginning, the Crab Nebula, was 11 light years across. This thing is 37,000 light years across. So this is we're talking about huge scales. So you get to this picture of stars forming out of nebulae. Stars burn for a few billion years where they produce a bunch of heavy elements. Then they explode as supernovae. The explosions themselves produce even heavier elements. Those elements go out and form a nebula, you know, the supernova remnant. And then it's kind of cyclical, where that nebula can then later on, after it cools off, condense to form new stars. And you get generations of stars in this way. Both high mass stars and low mass stars kind of do this. Whether there's a supernova or just a planetary nebula, in both cases, you kind of enrich the surrounding gas, and then it will eventually form a new generation of stars. And this is very important to bring it down to life on Earth. Here you see a picture of a protoplanetary disk. This is a very recent picture from the ALMA telescope. Really amazing. There is a protostar, I guess you would say, at the center of this, a star forming out of a cloud of gas. And you notice there's a disk around it with some orbits carved out. And those orbits are where the planets are forming around the stars. So in order to get those black rings, what you need is a little bit of those heavy elements, which can condense and form dust. Then the dust kind of accumulates and forms the rocks, and the rocks accumulate and form planets, etc. So what you're seeing is a system of planets forming around a new star. And this is only possible with those heavy elements. So this has to happen in at least like the second generation of stars. So in order to get something like Earth and our solar system, you had to have a lot of supernovae happening beforehand. So lastly, I'll come to the largest scales, cosmology, which is basically the study of the entire universe as one thing. To understand how supernovae can contribute to cosmology, I have to introduce the concept of the standard candle. It's kind of a funny name. I don't know why we use candle, but more modern version of a candle is an LED light bulb right here. The key concept is that, you know, if this is what we would have previously called like a 100-watt light bulb, which is actually only uses like 2 watts now or something, but a standard light bulb, if you move it further away, it's going to be fainter, right? It's going to appear fainter, at least. You know that that light bulb didn't change, it's still emitting the same amount of light, but just that it's farther away means it's not as bright. And in fact, we know that a light bulb that's twice as far away will be a quarter as bright. It'll appear a quarter as bright. So something 10 times farther away will be 100 times fainter. It's the distance squared. So if we were to put these light bulbs in distant galaxies, and we knew how much light each bulb gave off, we could use that to measure the distance to that galaxy. And now you just have to take this concept and replace the light bulb with a supernova. If there are certain types of supernovae that we know the brightness of, and in fact, there are some types that we know basically are always the same brightness, and we observe them in distant galaxies, we can figure out how far away those galaxies are. So for galaxies in some range, far enough away for there to be supernovae, but not so far that we can't see the supernovae, we have a good way of measuring the distance to those galaxies. I also need to introduce the concept of redshift, which in our situation basically corresponds to velocity. So if something is moving away from you, it is going to look redder than it actually is. If something is moving towards you, it's going to look bluer than it actually is. The analog here is if you've heard an ambulance or a police car drive by you, you know that as it's coming towards you, it's higher pitched. As it's moving away from you, it's lower pitched. And the same thing applies, that's for sound. The same thing applies for light though. The higher frequencies are if it's moving towards you, lower frequencies if it's moving away. And coming back to our idea of spectroscopy of astronomical objects, this just means that there's a shift in all of those lines. So by looking at the spectrum, you can see the pattern from the element it is, but you can see from how offset it is from our expected wavelengths, how fast that object is moving either towards or away from you. So again, you need spectroscopy for this. Spectroscopy is very important. By using these two quantities, the distance to galaxies and the velocity of galaxies, this is how we discovered the fact that the universe is expanding. So this plot here is called Hubble's law, named after Edwin Hubble, who kind of first posited this idea. If you plot the velocity of galaxies on the vertical axis, galaxies on the horizontal axis, you see that it's basically a straight line. And what that means is things that are farther away from us are moving away from us faster than things that are close by. So close by things are moving away slowly, far away things are moving away quickly. If you picture that in your head, what that means is you have an expanding universe where the things nearby are moving away slowly, things far away are moving away quickly. And in fact, we found out after, this is an old graph of just the original Hubble's law, but we found out later on that it's not a straight line forever. There is some point where it actually curves like this. That's the accelerating expansion of the universe, if you've heard about that. And this also, by the way, is where we got the idea of the Big Bang, because if the universe is expanding, you can play that video in reverse, right? It means everything originally was very, very dense. And so the idea is that initially there was some singularity where everything was in the same point and it exploded outwards and has been expanding to this day for about 13 something billion years. So bringing this back to supernovae, type 1a supernovae, these are the thermonuclear supernovae that I mentioned before, are standard candles. We've discovered that the expansion rate of the universe. But as I mentioned before, we still actually don't know why they're standard candles. We don't know why they explode. We don't even know actually what kind of binary system they're in. So it would be very nice to understand the tools that we're using to make these big discoveries. So supernova cosmology is actually a very active field as well. I talked a lot about supernovae, but in fact, there's many other really extreme, more extreme classes of transients that we know of today: gamma ray bursts, tidal disruption events, kilonovae, and even fast radio bursts, which I'm not going to get into because that could be a whole talk by itself. But gamma ray bursts, there are two different types. Some we think come from supernovae. And so it's a question actually, why do some supernovae have big bursts of gamma rays that come with them and some don't? Others come from merging neutron stars. If you have two neutron stars in a binary and they collide, they produce a burst of gamma rays. Gamma rays, of course, being the highest energy light that we have in the universe. We see these often, every day or so, but we know very little about them because they're very hard to observe. We have two main gamma ray observatories right now. They're both in space, and that's because gamma rays don't make it to the ground. They don't make it through our atmosphere, which is very good for humans because otherwise we'd die, but it makes it very hard to do gamma ray astronomy. The Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope, both very, very advanced technological machines that orbit the Earth and observe gamma ray bursts. tidal disruption events. This is a really crazy one. People love this stuff. So I'm about to show you, you see these two little points of light in each of the two panels on the left-hand side and the right-hand side. I'm going to show you a top-down view and an edge-on view of this system. What you're seeing is a star orbiting a black hole in both cases. And I'm going to show you what happens if that star gets a little bit too close to the black hole. So here goes the animation. You see what's happening is the star kind of gets ripped apart into the stream, which then orbits the black hole. And then finally, you see the stream actually collides with itself and makes all flashes of light at different wavelengths in the night sky. So we've seen now things think tidal stars getting disrupted by tidal forces near the edge of a black hole. But again, this is a very new field, and we don't understand much about the physics that's happening here. The conditions are very extreme near these black holes. Last crazy type of transient I'm going to tell you about is a kilonova, which is a merger of two neutron stars. This was discovered very recently, just in the past 5 years. What you have here is two stars which are extremely dense, made purely of neutrons, orbiting each other, and eventually they will collide, and they form these, first of all, a really big explosion, which is the kilonova. And you may notice all these ripples coming out from it. These are not, okay, these are actually gas ripples, but those ripples you saw at the beginning were ripples in the fabric of space-time itself. So they're producing what we call gravitational waves, which were just observed for the first time in 2015. I could give a whole other talk about that. The technology behind detecting gravitational waves is really incredible. But what we now know about type of stellar explosion that which produces a lot of radioactive elements and glows because of that energy that was released. So come back again to this periodic table, which shows you where all the elements came from. Now I've explained to you where all of the purple elements come from. We think those are all produced in neutron star mergers. The only thing I didn't talk about was like those dark brown ones, which were only produced by humans. So we don't know of anywhere in the universe that produces those. So basically, other than hydrogen and helium, almost everything on this periodic table is somehow related to stars and their explosions, produces all the heavy elements in the universe. So to summarize, studying supernovae and other transients is a pathway to learn about all the basic properties of the universe, all the way from the smallest scales to human scales to the largest scales of the whole universe. So I'll end here with a little bit of discussion just about how we actually do this. This is really what I do on a daily basis. We call this time domain astronomy because it's things that change kind of on human time scales, things that we can watch change in the sky, not just a static galaxy, not just a static star, not just a static planet. The real issue is that the rates of all of these things are very low. So for example, in the Milky Way, we only get a supernova every 100 years or so. It's actually been much more than 100 years in the Milky Way. So if I'm a human being and I want to study supernovae, then I have a problem because I don't live 100 years. So I need to do something. Otherwise, I'm going to discover at most one supernova in my lifetime. The answer is we want to look for them in lots of other galaxies, right? As many galaxies as we can. So then we run into a new problem, which is that all of those other galaxies are pretty far away. We can't see the individual stars in the other galaxies for the most part, with a few exceptions. And that means we don't know which ones are going to explode. Just scan the entire sky all the time and look for changes. Now, this is much easier said than done, but there's a whole industry in astronomy now devoted to just looking for things changing in the sky. One example, local to you all in Southern California, is the Zwicky Transient Facility. This is done at Palomar Observatory in northern San Diego County, out in the mountains there. This is a picture of a 48-inch diameter telescope at Palomar, which just scans the whole sky basically every night. What you're seeing here is like a map of the sky. It works the same way as a map of the Earth, but just looking up instead. And you can see it avoids this region where the Milky Way galaxy is, because you can't see most stuff beyond the Milky Way galaxy there. But for the rest of the sky in the northern hemisphere where it can see, it just continuously scans across there and builds up data on all of these areas. So then we have to look for changes. We have a new picture where there's a point of light here in a nearby galaxy. That's a supernova. We have a previous picture of the same field where there's no supernova there. And so we can just subtract the old from the new to see, oh, okay, this is what the supernova looks like. And you can do this. The reason I'm pointing out this subtraction is that humans don't have to search through all of these. You can do the subtraction automatically with computers and find these new sources in the sky. Now, there's a problem you might have noticed, which is that there's all this other stuff in this image, which is totally not real. Image subtraction is very complicated because the conditions at the site change with time. They change between different sites. So you won't ever get a perfect subtraction, and you have to know which are real and which ones aren't. Computers are kind of okay at this, but a lot of times humans are still involved at looking through these types of things. So once the Zwicky Transient Facility finds supernovae, they actually just report them publicly on some website. You can go look these up if you want to, but they just say, hey, we found a new point of light at these coordinates, probably a supernova. This is how bright it is. Tells the rest of the astronomical community, this is where you should look. So then comes my job, where I want to get a spectrum of that thing, as I mentioned, and I want to get a spectrum as soon as possible. Remember back to how I said that things happen only on like day time scales, and you really want to catch it during that time. And the problem is, the sun's always in the way of half of the Earth, so you won't be able to observe during that time. So the way to ensure that you're going to get observations as soon as you need them is to put telescopes all over the Earth. I often use this facility called Las Cumbres Observatory, which is based up in Santa Barbara, but they have telescopes on many different sites, tall mountains all over the world, in Chile, Hawaii, Texas, South Africa, Australia. So one of these will always be in the dark. And so they're all also robotic telescopes, and they're controlled remotely through the internet. So I can just go onto Las Cumbres Observatory's website, fill in an observing request, say I want to look at this supernova, these are the coordinates, I want a spectrum this long, and I request this observation, and many times, unless there's bad weather or something, I will get that spectrum very quickly, and then I will report again the rest of the astronomical community that I got this spectrum. This spectrum has these elements in it, therefore it tells me it's this type of supernova. Some cases more interesting than others, but many people have different scientific interests within this supernova field. So they may say, oh, this is a type 1c supernova. I'm very interested in getting more. Getting to here is that getting an era of big data in astronomy, right? This is no longer somebody goes up to the observatory for a few days, looks through a telescope with an eyepiece, draws a picture of a galaxy, and tries to understand, what is happening in the galaxy. We're talking about every night, this survey that I mentioned produces like a terabyte of data, which is like hundreds of thousands to millions of new sources of light. So by sources of light, I mean, this includes all that junk, which is not real, actually. So you have to sort through those. You get 1,000 to 100,000, which are probably real. And maybe 100 of those are bright enough to be worth following. Dozens of them can be scheduled for spectroscopic classification with the spectrograph. And a few of those turn out to be very, very interesting. So now that, discovering the pretty routine. We discover so many per day. It's not even possible to observe all of them in detail. We really rely heavily on telescopes, software, both to control the telescope, process the images, and find the transients, internet to control and to report the results to the rest of the community in order to study events. I think this is actually one of the coolest and least appreciated aspects of time, is that this technology has not been available for very long. So it's really just in the past decade or two that we've had the hardware, software, and communications capacity to do all of this stuff. And that's why there's such an explosion in the study of supernovae right now. So with that, I'm going to end my talk. Thank you so much for listening. I'm happy to take all of your questions.
Thank you very much, Griffin. Very interesting and very nice path that you took us, letting us know about every detail. That was great. And I hope you see on your screen the kudos is coming your way. Thank you very much. So I'm sure there are going to be a lot of questions. So the floor is now open for you to use the Q&A and send the questions. Oh yeah, a lot of kudos is coming. Great.
Yeah, I see this. I've never seen this in a Zoom webinar before. Pretty exciting.
Reza?
Yes.
Can I say that our club observatory over the years has discovered either 3 or 4 supernovae?
Sure, 3 or 4.
Yeah.
No, that is really cool. There's actually, I know I think Reza's alluding to the fact that I was talking about discovering hundreds of supernovae, but in fact, the amateur astronomy community all over the world is always finding interesting supernovae. And they actually, in some cases, will report them to the same websites that we use to keep track of them. And amazingly, they're still finding some of the most interesting things that we study. I wrote a paper recently with the amateur astronomer from Japan who actually sent me his images he took with his camera, and we analyzed them and wrote a paper about it, and he became an author on the paper. It was really amazing collaboration.
I discovered one of those 3, and that was 1994 I in the whirlpool.
Nice.
Me and some other guys. There were several people discovered at the same night. But that was back in before there was only 1 or 2 survey programs doing anything, and we discovered it on Good Friday night on April 1st. So competition was pretty low.
Yeah, that was a little bit before I was in the game for astronomy.
Yeah. Nowadays, well, my question on the bottom was going to be, what impact will the Rubin telescope have on all this?
Yes, that will. All of those huge numbers I just showed to you will increase by many orders of magnitude when Rubin Observatory comes online. So the effect is just we will find now millions of transients every night instead of 100,000 or something like that. And we will have, so in one sense, it's great. We're finding so many more things. We can understand what the populations of supernovae look like. On the other hand, it actually poses quite a challenge, which is that we have to find the most interesting things within those million transients. And actually, a lot of the stuff that I have worked on in the past few years is, for example, machine learning algorithms, which can sort through all of that data and try to figure out which things are likely to be interesting that we can get spectra of, because we just don't have enough telescopes with spectrographs to get spectra of all of them.
Perfect. So let me start by actually mentioning the tool that you said that you're using, Las Cumbres Observatory, because our club has also a proposal there, but we are allowed access to their educational telescopes, which is, well, much smaller than the ones that perhaps you're using. But let me tell the audience that if you're interested in using those telescopes and do similar research, the club has a program called Cosmic Adventures. You could find more information about that on our website. Now, the question is, how happy or satisfied are you with the Las Cumbres Observatory? You do all your follow-up observations with that?
I don't do all of them with that. It may interest you to know I'm literally sitting inside of the headquarters of Las Cumbres Observatory right now because I am visiting them to do some collaboration this week. But don't worry, there's no one here listening to me, so they won't know what I say about them. I really love using Las Cumbres Observatory because it is one of the few facilities that I can very quickly trigger a telescope somewhere around the world, like within minutes if I need to. And that is really critical for my research. So I often use them, but they're not the only ones. Of course, being in Arizona, we have a lot of telescopes also in the mountains around Tucson. And I often go up to Kitt Peak, for example. There's a 90-inch telescope there that I use for spectroscopy. There's also the MMT, which is a 6.5-meter telescope, much larger, which we can use to get spectra of faint objects. There's also the Magellan telescopes in Chile, which I've sometimes used, also 6.5 meters across. So it's a combination of smaller telescopes, which can rapidly get observations, and bigger telescopes to get things as they fade away.
And for the skies, for the main source of getting the choosing your object, you use the sky surveys. The Zwicky is the main thing that you refer to, or are there a couple of sky surveys that you use to get the initial confirmation?
Yeah, there are several. Right now, Zwicky is the largest one by numbers, but there's also Atlas, which operates out of Hawaii. Their main job is to look for near-Earth asteroids that may hit the Earth and cause problems for us, but they a lot of times find supernovae as well, and they report them. There's the Pan-STARRS survey, which also is in Hawaii, very active. There are even sometimes things discovered by the Gaia Space Telescope, which is meant to look for planets, but they sometimes find supernovae there. Everybody just accidentally finds supernovae sometimes. And in fact, we run our own survey at the University of Arizona as well. It's a much smaller survey, but it has the advantage of having very, very high cadence. So we have a telescope in Chile and a telescope in Australia, and we just observe every nearby galaxy every night. So at both sites. So that means we have about 12-hour cadence. So if we discover something, and it's in these nearby galaxies, so you can observe things very early when they're still faint. If you discover something, it means it's about 6 hours old, which is really the key time that we want to access to understand what is the environment right around the star. We call this DLT40, which is the distance less than 40 megaparsecs survey. And we don't find a lot of things, but the things that we find are really exceptionally interesting because no one else can find things that early for the most part.
And speaking of time domain astronomy, just to get a feel of how you conduct your research and how's a day in your life doing research. So are you always on call for exciting objects, or is it like, okay, let's miss a couple, that doesn't matter, let's choose one that's more interesting? How's your research?
Yeah, you do kind of have to be paying attention, right? Of course, I'm not the only one in my research team. There's several of us, so I'm allowed to go on vacation if I want to sometimes, but because other people will be there to fill in for me. But yeah, it does. Occasionally there will be something, if we discovered a really interesting supernova on Friday night, and you really want to get data of it, sometimes you'll have to run home and start scheduling observations as soon as possible, no matter what's happening, or do it from your phone, which is even easier sometimes. And especially, I don't even want to get into what happens when there are gravitational waves. This is going to happen very soon again. The gravitational wave detectors will turn back on and we'll start finding kilonovae again. That's really quite a hectic field to be in, because you really have to drop everything you're doing and get observations instantly. So there is some aspect of that. Of course, it does. Yeah, it doesn't ruin my life, if that's what you're asking.
Okay, great. Thank you. Nice to hear that. And speaking of gravitational waves, so we know these are very, very extreme events. Now, as we get further away from this phenomena, the effect drops with R squared, right? So when Betelgeuse explodes, are we expect to feel anything on Earth, or is it just the instruments that are going to be able to detect it?
You're speaking specifically about gravitational waves?
Yes, that's the question.
Yes.
Yeah.
So I actually worked with someone to study this. Betelgeuse, no, I think we will not detect. Well, okay, Betelgeuse, we would detect it if Betelgeuse were to explode. But basically only things within the Milky Way galaxy we would be able to detect gravitational waves from a supernova. Maybe if you have some very good computational techniques, you could also observe gravitational waves from supernovae in the nearest galaxies to us. We're talking about like, the nearest 1 or 2 galaxies. But beyond that, it's essentially impossible to observe the gravitational waves with our current gravitational wave detectors because they're very weak.
So that's for supernovae. And what if we have a merger? How close to a merger should we be to maybe feel something?
To feel something, I think you would probably never feel something as a human, but because the detectors are very, very sensitive to minuscule changes. The different, the contractions and stuff of space that we're measuring are like less than the size of an atom, 1,000th or something like that. So we would not notice it as human beings, but we can detect these things very far away because these are very extreme events. They really affect, they have strong gravitational forces. So we can see things, I don't remember the number off the top of my head, but I'm thinking it's something like 600 million light years away with the current detectors. I have to check the numbers, but something like on the order of hundreds of millions of light years away. So that is a significant fraction of the universe, actually.
Perfect. So way beyond the stuff that happens within the galaxy.
That's right.
And there is a follow-up question. I'm not sure if I understand it correctly, talking about the strange quarks. What happens to them when 2 neutron stars merge, producing strangelets? Is that something that you would comment on?
I'm not familiar with this. I think even when neutron stars merge, quarks I'm familiar with. Quarks are the particles that make up neutrons and protons. But even when neutron stars merge, the quarks never escape from the neutrons, as far as I know. So I think you get some nuclear reactions there, but it's only from the neutrons and protons. It's not from, you never release quarks in them.
Perfect, thank you. And next question is about the diagram of red giant supernovae that you showed, which appears to be a shock wave to the left, not to the right. Can you speak to the asymmetry here?
Yeah, this is one of the things I mentioned, is that there may be asymmetries that we don't understand. But I think in this case, what you're seeing is actually material that is outside of the star, like this big bar on the left-hand side and this kind of shell, where the stellar winds are hitting the ambient material in the interstellar medium and causing these shocks. But it's not necessarily the same on one side of the star as the other. So these things that you're seeing were not part of the star. The things very in the center maybe were part of the star, but the shock waves that you're referring to don't necessarily come from the star. And I think it's just the wind from the star kind of driving shocks into that material.
Thank you. And for the novice of us, there are several different types of supernovae, as only some of them can work as a standard candle. Can you talk a little bit about different types and how different they are?
Yeah, as I went, let me go back a few slides. The main 2 types are core collapse supernovae. These are the explosions of massive stars, where this was the process I described, where like the iron core collapses and the material gets expelled outwards, versus thermonuclear supernovae, which are explosions of white dwarfs in binary systems. So these ones are the ones that you can use for standard candles, the thermonuclear supernovae, the white dwarf explosions, whereas the core collapse supernovae are not always the same luminosity. So you cannot use them as standard candles. I don't know if you've heard, maybe you've heard the like astronomer jargon. This is a type 1A supernova.
Yeah. So type 1A, 1B, 1C.
Yeah. So type 1As are the white dwarf explosions, which are the standard candles. Type 1B, 1C, and type 2 are all different types of core collapse supernovae.
Perfect. Thank you very much. And speaking about the emissions or the spectra of supernovae, absorption, emission, and you mentioned about the iron one being from the material outside, not inside, if I recall correctly, and because you do not expect any iron to be on the within the star, the specific star that explodes. And you mentioned we have emission spectra of iron. Yeah, I believe that was the slide that you were mentioning.
Talking about this one, yeah.
Yes.
So not iron, but actually like the elements I was talking about here are like nitrogen, oxygen, and carbon. You can kind of see them there. NO and C. And H is hydrogen.
Perfect. So we see an emission spectra of the stuff, not an absorption. Is that because they get heated up from the energy that was received from the supernova?
Yeah, that's right. Emission happens when, so you kind of ionize an atom, and then it recombines, and when it recombines, it releases light. Whereas absorption happens when you have light coming from behind the supernova, from behind the gas, and it gets absorbed by that atom, which can then potentially ionize it. So if there's a source behind it, it can be absorbed, and then it will potentially re-emit that light. So you see both things happening depending on exactly the conditions, the densities, and the geometry of the situation. In this situation, we see purely emission because it's the ionization of that material that we're seeing. Whereas in some cases, you also see absorption. For example, right, if you can see, this spectrum shows both emission and absorption. You can see it goes down and then up here, which is coming from different parts of that sphere of material.
I exited completely. I said it killed Zoom completely and restarted it.
Alan, you're live. We can hear you all good. Okay, I guess. And speaking of then again, emission and absorption and emission spectra, I believe there's a question that wants clarification. So can you speak to the fact that the spectra of each element is the signature of that element and it never changes, right?
Mm-hmm. That's right.
And so the two things that are changing are the intensity of the light, and then we observe the shift due to them going away or towards us.
Yeah, you can see, so you can see, the brightness of the supernova will go up and down, and the velocity of the material will go down gradually, which will shift the light more to the red as it decreases.
And we have a request for you to go back to the slide that showed layers of fusion elements.
Yes, this one. I can go all the way through them again.
Yeah, that should be it. If the questioner wants another slide, they could mention again. And then there is this other, perhaps ask for comments, is that there was in the news, they have also included a link, there has been a gamma ray burst, and that has caused similar effects to solar winds on Earth. Have you heard the news? Do you have any comments on that?
I have heard this actually, yeah. I was just talking with some people about it recently, but just to get observations, I don't personally study gamma ray bursts, so I don't know a lot about it, but I think the idea was just that it was very nearby, and therefore the level of gamma rays that hit the upper atmosphere potentially caused some disturbances in the upper atmosphere. Of course, this doesn't actually affect us on the ground very much, but we do have stuff up there in the upper atmosphere. And so it was detected. That's all. It was just a very, very nearby gamma ray burst. So we got a lot of gamma rays from it.
Okay, perfect. Thank you very much. I have gone through all the questions so far. Let me ask from people on the panel or people from the Chapman. Are there any questions from our speaker tonight? So if not, that's it. So I would like to thank everybody for attending. And again, thanks our Griffin for a wonderful, great talk. And with this, I would like to mention that you would please check our calendar on the website for all our upcoming events at ocastronomers.org. Thank you for joining us and we wish you great times ahead. And good night, everybody.